Hi everyone, welcome back to this session where we are going to solve the problem 4 in the ANSYS. Now once again this is the statement of the problem, a compound bar loaded as shown in the figure. Now once again we need to find out the nodal displacement, strain, stress and the reaction at the fixed support. Here also we are going to consider the two different material, that is the steel and the copper, and respective Young's modulus values are mentioned. Now here both the ends of the bars are fixed and the force is applied at the junction. Now before moving to the solution in ANSYS, let us see the values what we have calculated in FEM. So these are the values we have calculated in FEM, where the displacement at node number 1 is fixed. I mean it is fixed, therefore it is 0. Similarly, displacement at node number 3, that is the fixing condition which is there on the extreme right hand side, therefore there also it is 0. Now whatever the displacement I am going to get, I will get the displacement at the junction, and that value is 0.104373 mm. And similarly, when I calculate the strain in the steel portion, it is 1.3 into 10 to the power of minus 4, and similarly strain in the copper portion is minus 2.087 into 10 to the power of minus 4. So this negative sign because there is a compression in the copper. Similarly, the stress in the first portion, that is steel portion, is 26.09 Newton per mm square, and the stress in the copper is minus 20.87 Newton per mm square. Once again, that negative sign is because of the compression in the copper. Similarly, when I see the uh, reaction at the steel end, it is minus 73,770 Newton, and reaction at the copper is minus 26,228 Newton. So adding these two together, it is equal to the applied force of 100 kilonewton. Now let us solve this problem using ANSYS. Then we will came back and will cross verify the values what we have calculated using FEM, and using software, ANSYS software, whether the values are matching or not. So before begin, so let us make this screen visible the white, so that it is very easy to see whatever the things I am doing on the screen. Okay, now as it's a uh, structural analysis, so that I need to select under preference. So go to the preferences, select structural. Okay, then I need to come to the preprocessor where I can define the element type, real constant. Then I can model the problem. Then I can do the boundary condition and loadings. Then I can solve the problem. So first, under preprocessor, I need to go to the element type. So I need to select the element which is required for the analysis. So it's a one-dimensional bar problem, therefore I need to select it as a one-dimensional element. Therefore I'll go to the add. So add, so link is the my one-dimensional element, therefore I select link and I say okay, and I'll close this element type. Once the element type is defined, now I need to give the real constant for whatever the element we have uh, created. So real constant, add add the real constant for that link element. Okay, so first cross sectional area is for steel. I'll start from the left hand side. So first I'll get the steel, then I'll get the copper. Therefore I'll give the uh, value for the area value for the steel, where I have given the diameter. So when you calculate the area, it is pi by 4 into d square, that is pi by 4 into 60 square. It is a 2827 point something. So let us take it as a whole number. So it is 2827 is the value. I'll say apply. Similarly, I need to calculate the uh, uh, I mean area for the second portion, that is copper portion, where I given the diameter as 40. Therefore it is pi by 4 into 40 square, and that value comes around 1256 point something. Therefore I'll enter it as a 1256 and I'll say okay. So these are the two sets of real constants are defined. Set 1 is for steel and set 2 is for copper. That is what we need to remember. Then I'll go to the metal property. I need to define the metal property. So under metal property, I'll go to the metal models. Then I'll go to the structural. Under structural linear, it's a linear material and it is elastic material and it is having an isotropic value. So I'll give the Young's modulus for the steel first. That is 2 e raised to 5 is the value for Young's modulus that I'll mention here. Then Poisson's ratio, as it is a one-dimensional analysis, I'll keep the Poisson's ratio 0 and I'll say OK. So this is the first metal model I have defined. Similarly, I have one more metal. For that, you go to the metal at the top here. Then you select new model and it will automatically give the number 2. Then you say OK. So now for the metal model 2, I need to define the isotropic value, metal value, that is for the copper, and that value I given 1 e raised to 5 is the value, and Poisson's ratio as one dimensional, I'll take it 0 and I'll say OK. Now only there are two metal, I defined both the metals. Now I need to exit this. For that, you once again go to the metal and say exit. Now once the metal property is done, next I need to create the modeling. For that, I'll go to the modeling, create. Now I need to create the nodes. I'll click on the nodes. So those nodes I need to create in active coordinate system. So you click on the active coordinate system. So let us define the first node. The first node I'll always take it at the origin. Therefore it is x0, y0 and z0. So all the x, y, z I'll put it 0 so that it will come on the origin. I'll say apply. Because I need to create two more, I'll say apply. So then I'll change the second node number 2, node number 2. Then I'll give the distance. Now what is the distance? Now from node number 1 to 2, that is my steel portion, which is having a distance of 800 mm. So I'll give it as an 800 and I'll say apply. Similarly, I need to create the third node, and that distance is 1300 because the distance is calculated from the origin, but the copper portion is having a length of 500 mm. But as we are calculating from the origin, therefore it is 800 plus 500, that is 1300, and this is the last node. Therefore, I'll say OK. Now these are the three nodes we have created. Now I need to create the element between these three nodes, but the element which is there between node number 1 and 2, it is a steel element, and whatever there between 2 and 3, it is a copper. So while creating this element, I need to uh, take the values of steel, that is area of the steel and Young's modulus of the steel I need to select. Then only the steel element will be created here. For that, I'll minimize this node. I'll come to the elements. So in the elements, I'll go to the element attribute. Then I know the metal number 1 is for the steel and metal number 2 is for the copper. So I'll select metal number 1. Then real constant set number. If you go back and see, the set number 1 we have created for the steel and set number 2 we have created for the copper. Therefore, we'll consider the real set number 1 for the steel. So that is what I have taken it as 1 here and I will say OK. Now both the values of area and Young's modulus are taken for the steel. Now I'll go to the auto numbered through nodes. Select node number 1 and 2 and you say OK. Now first my steel element is created. Now I need to create the copper element. For that I need to take the area of the copper, Young's modulus of the copper. For that once again I'll go to the element attribute. Then I'll change the metal number to 2, that is Young's modulus is 1 e raised to 5. Then real set I'll take it as 2. Therefore area of copper is considered. I'll say OK. Now I'll go to the auto number through nodes. Select node number 2 and 3 and you say OK. Now once this is done, my work of preprocessor is over. Now I need to, still I have to apply the loads. So I'll go to the loads, define loads, apply structural. Under structural I need to apply the displacement. Now displacement will be applied on the node. I'll select on node. Then I'll select node number 1 and I'll say OK. So it is completely constrained, therefore I'll say alt div and I'll say OK. Similarly, my node number 3 is also constrained completely. So I'll select on node, select node number 3 and I'll say OK, alt div OK. So I have done individually, but you can also do simultaneously by selecting node number 1 and 3 and you can apply the alt div. Similarly, I'll go to the force on node So node number 2 is applied with the force of 100 kilonewton. Therefore, so I'll say OK, and it is asking in which direction the force is applied. It is in x direction, and the value is 100 e raised to 3. So that is the value I am going to enter, and I'll say OK. Now all the boundary condition and force is applied. Now the work of preprocessor is done. Now I'll go to the solution. Means my problem is ready to solve. I'll go to the solution. Solve current ls. Okay. Now it will do the solution at the back end, and it will give the result. I mean, message that the solution is done. Now once the solution is done, you close this. Then you come to the general processor, where you can check the results. So in that you can go to the least result, nodal solution, DOF solution. As applied force is in x direction, I'll get the displacement in x direction. So therefore you select x component of displacement. Okay. So the displacement at node number 1 is 0 because it is completely constrained, and displacement at node number 3 is 0 because it is completely constrained, and the displacement at node number 2 is 0.10439 is the value. Now I need to similarly check the values of stress and strain. For that I need to define the element table, define table, add, pull this down, select by sequence number LS, that is line stress. I'll take it as number 1, apply. Then once again pull this down by sequence number. I'll take it LEPL as second result, and I'll say OK. These are the two results I have ordered, that is stress and strain, and I'll say OK. Then I'll once again come back to the release results. Then I'll go to the element table data. Then you select LS and LEPL and you say OK. Now once again I have two elements, therefore it has shown two elements. The stress in the first element is 26 point something. The stress in the second element is minus 20. Negative sign once again because there is a compression in the copper. Similarly, strain in the first element is 0.130 into 10 to the power of minus 3, nothing but it is 1.30 into 10 to the power of minus 4, and minus 0.20 into 10 to the power of minus 4. I mean minus 3, nothing but it is minus 2.08 into 10 to the power of minus 4. That is what the stress and strain I am going to get. Similarly, I need to check the values of reaction. So I have two reactions here because both ends are fixed and both are in x direction. Therefore, I'll consider structural force effects and I'll say OK. So it will show the location where the reaction is there. Node number 1, I have one reaction which is 73,777 Newton, and at node number 3 I have minus 26,223 Newton, nothing but 73 kilonewton and 26 kilonewton. Adding these two, I'll have 100 kilonewton. So that is what the reaction we have calculated. Now I'll come back to the my presentation. There we can compare the values here. So whatever the values we are done with FEM, now I am getting the same values with the I'll getting the same values with the ANSYS software. So if you compare, all the values are same with the sign. With the sign I am going to get the stress is 26 in the steel, minus 20 in the copper. Even the reactions are also I am getting the same values. Now this is how you need to solve the a bar problem where both ends are fixed. Thank you.